So, good morning, everyone. Welcome to Madrid. My name is Dario Fiore, and I'm the General Chair.
My name is Isabel Gonzalez, and I'm co-chairing this.
And my name is Ignacio Cascudo, and I'm also a co-chair.
So, it's a pleasure to welcome you in Madrid for Eurocrypt 2025. So, we'd like to share some opening remarks. So, let's first see what are the numbers this year for Eurocrypt. So we have 657 registered attendees and probably a few more after yesterday night. So out of which 256 are students, and I'm proud to say that out of these students we are funding 102 of them. In particular, 65 are funded by ICR, by the funding for student presenters, and 37 are funded by our sponsors. So all of you and all of us, we come from 41 different countries. Eurocrypt, as in the last years, is also featuring affiliated events that happen during the weekend. We had 12 affiliated events, and they gathered 451 attendees. So let me now share some logistic information. So these are very important things to remind for the next days. So you made it here, so you found your way to the plenary room. That's already a good goal achieved. So let me remind you that there are two ways to enter the Congress Center. So you can enter from the hotel lobby, or you can enter from the Congress Center entrance. And the recommendation is to use the Congress Center entrance, okay? So, and the venue is like this. So we are on the 4th floor. This is the plenary room, right? So, and this is also the room where the track 3 will take place. And Madrid 1 and Madrid 2 that are down the corridor that way are the rooms where track 1 and track 2 will take place respectively. So another important thing on the okay, so how do you enter? So if you come from the street and you come from the hotel lobby, you actually end up in this staircase B, or the elevator that is right in front of this entrance. And if you come from the Congress Center, you will end up there. And these are the entrances of the room. I mean, you will find your way. So registration desk, and it's also an assistance desk if you need any help, is located on the 4th floor, more or less around that exit. Important, so if you want to eat, lunch is going to be on the same floor. So on the 4th floor is across the corridor. So you exit the room, follow the volunteers and the signs, and it will be quite easy to reach it. But, you know, be patient. We are many people, so also be patient for the space. We are, really, we are at almost full capacity. Okay, so more things about the space. So the coffee breaks will take place on the 3rd floor. So it's the same space where we had the welcome reception yesterday night. And we also advise you to use the coffee break area as the so-called hallway track. So if you want to hang out with people, chat, the space is for us. But please don't use the space on this floor because the corridors are a bit narrow. So it's much easier if we don't create bottlenecks. And also, we created a sort of co-working area at the corner of the coffee break area, where there will be chairs and tables if you want to work more quietly. Okay, how do you move across floors? It's kind of easy. There are 3 staircases, so you will find them at the exit of these doors. It's follow the signs, follow the volunteers. After today, you will become a master of this venue. It took us some time, but you will make it as well. Yeah, and again, remark, don't stand in the corridors, please. Everybody's collaboration will be helpful. So let me hand it to Maribel.
Okay, thank you. So now that you know your way around in the venue, so Okay, here we are. I'm happy to announce some special events that we will be having. Of course, we will have a RAM session that's going to happen in association with Midnight, and that will happen tomorrow evening. On Tuesday, you have until noon, until 12, to submit your funniest, more musical talk ever. The chairs are this year Karsten Baum and Bernardo David, and I've heard they're preparing nice surprises. And this will happen here, where we currently are. So it's easy to find now that you're here. And an important thing is that we will have food and drinks in 2 breaks, and they will be given across the corridors in the Cervantes area, in the place where we will be having lunch today. And we're advised not to bring food or drinks into this area, into the conference room. So I would, of course, we would appreciate if you can remember that tomorrow evening, right? So please submit. You know how to do it. You have a QR code there. There's information on the webpage. So please do it. Again, another nice thing we will be having is the banquet, of course. This will happen on Wednesday evening, and we will use all the space that's normally used for talks, namely this Madrid 3, 4, and 5, where we currently are, and also Madrid 1 and 2, which is there. Everything will be open, and we will have the banquet here. Only one important reminder is that those who have special dietary restrictions should come a bit earlier, namely at 7:30 p.m. And we will give them a label there at the entrance of Madrid 3. You have a label there which says "Do not feed," so please be early in case otherwise you may end up with that one. And place this label near your plate so that the waiters know of your dietary restrictions. And furthermore, we will be having 2 very exciting community events on Wednesday. First, Women in Cryptography and Alice are meeting in the rooms Princesa and Colón. That is, Princesa is the co-working space, so I hope you identify it fast. It's on the 3rd floor in the coffee break area. And they will be there from 1 to 4 p.m. This is only for those who have registered with them at the Women in Cryptography webpage. And also we're having a very nice event at the other corner of the hallway track, so downstairs, right opposite to Princesa, in the room called Callao. This is Cryptography in a Changing World, Navigating Geopolitical Uncertainty and Security Risks. And this is organized and chaired by Kenny Patterson and Martin Albrecht. We have limited space, so please contact them or make some noise if you want to attend, or be sure to be there early. Okay, so now, Nacho.
So if you have any questions, emergencies, and so on, the organizers and the helpers are the ones that we have a green lanyard. The registration desk, as Dario was saying, is on the 4th floor here and in the exit. Please wear your badge at all times so that the staff at the hotel can see that you are attending. The food is labeled for allergies and dietary restrictions, so if you are in doubt, ask us or the waiters. We have also, maybe you haven't noticed, but somewhere in the webpage there is a guide with some travel tips and things around this area, so that maybe you are interested in doing some tourism or other things. And well, the Wi-Fi, here you have the password. I will not say it because it's someone could be hearing it. So by registering, you have accepted to abide by the code of conduct of IACR that, basically ask us to not, harass and discriminate and the participants. One thing that you should take into account is that, as you could see, the red lanyards signify that people don't want to be taken pictures. So please respect that. And if you have any experience of harassment or discrimination, please reach these people here. So us3, Sofia, Alison, or Michelle, and you have also here a QR code with all the information and contact data. So I think, this.
Yeah, so before starting the session, I would like to conclude these opening remarks with a few thank you. So first of all, we should thank the program committee chairs for, together with the program committee that involved many people, 118 committee members, 10 area chairs, and almost 560 sub-reviewers. We should thank them for this program. They did a lot of work over the past months, so let's do a round of applause for them. So more thank you. So like, first of all, personal thank you to Julia and Damian Stelle for sharing many tips about previous Eurocrypts. So, this is great, and we should communicate more about general chairs. Also, Felix and Christina for, sharing their experience about affiliate events. It's a new thing at Eurocrypt. Sharing experience is very helpful. I want to give thanks to many people from ICR, like Michelle, Bertram, Brian, Kay, Kevin. You have no idea what these people do until you are a general chair, and they do a lot of work, and ICR is possible thanks to them. So let's do a round of applause for them. And further thanks to Iago Antolin from Universidad Complutense, who helped us during the affiliated events, and to Daniel Benarroche, that was our sponsorship chair from Inverstech, who helped us with the sponsorship. So, and finally, I want to give a really, really, really special thank to the local team. And also to our supporting institutions, IMDEA and Universidad Carlos III, like a special thank to IMDEA for giving us a great support during the last 2 years to prepare this event. Without them, we would not be here. And without all the people in these slides, you will not be here. We will not have badges. We will not have many things. So I think these people are doing an amazing job. They are working probably from the sunrise until they go to bed these days. So we should give a really great round of applause to the local organizers. So final thanks to the sponsors that made us, help us with the financial part of the conference, like the registration fee is not that high thanks to them, so thanks to the platinum level sponsors, the gold level sponsors, silver and bronze. Thanks to them, we reduced registration fee. We could support all these students to come here to Madrid. And finally, so enjoy Eurocrypt, enjoy Madrid, and let's start with the scientific program, which is why we are here. Thank you.
Good morning and welcome to this first session of the conference. My name is Serge Fehr, and together with Pierre-Alain Fouque, I was a PC chair of this conference. So we're going to chair this session together because this is a special session. It's the session of the awarded papers. So the first 2 papers to be presented will receive a Best Paper Award, and the third, the Early Career Best Paper Award. So these awards will be handed over formally tomorrow during the IACR award ceremony. Today we're going to concentrate on the scientific content of these papers. I'm now handing over the mic to Pierre-Alain to introduce the first talk.
Thank you very much, Serge. So the first talk will be given by Hugues Randriambololona from ANSSI. So it's a French national agency in security. And it will be about Michaelis, a new distinguisher on Michaelis. And so, Hugues, the floor is yours. Thank you.
Okay, thank you. So do you hear me? Okay. So the title slide already contains the 2 main ingredients of the talk. So I will talk about CZGs. I will explain it a little bit later. And another ingredient is shortening. So that's why I use the shortened version of my name. So, but now we will not shorten names, we will shorten codes. So our motivation is the Michaelis crypto system. So Alice has some structural secret data. She uses it to produce a public code, that is a binary GOPA code. And at the same time, she has a decoding algorithm for this code. She keeps it secret. So Bob, in order to send a message to Alice, he encodes it as a code word, and he adds some noise. So he sends a noisy code word. Alice, thanks to the decoding algorithm, she's able to recover the message. But now for Eve, so when she sees the code, we think that the generator matrix of the code, it doesn't leak the secret data. And so she treats it as a generic code. And now decoding a generic code, it's a hard problem. So in more detail, so this decoding problem is very well studied, and it has a basis of code-based cryptography. On the other hand, the first problem, related to the security of the key, it's a really ad hoc problem, and somehow we will see that it is similar to some trapdoors in multivariate cryptography. So I like to say that somehow Michaelis invented code-based cryptography, but at the same time, he somehow invented multivariate cryptography. So what is the state of the art of the cryptanalysis of Michaelis? So this is a slide that I stole from the classic Michaelis team. First, concerning message recovery. So the best attack is by what we call information set decoding. So the complexity is of the form is exponential in n over log n with some constant. And there were decades of studies of this problem, but the constant it was not improved. So, but there is another problem that is the security of the key. So either we can try to recover the key or only to distinguish it. So this is an easier problem. And so it is somehow discarded by the proponents of Michaelis because its complexity up to now, it is more than exponential in n over log n. So there were some results, but these results, either they needed the code to have very extreme parameters, or sometimes also they replaced GOPA codes with other types of codes. And in this case, it was possible to recover the key, but with GOPA codes, there was nothing. So in this work, we will not recover the structure, we will only consider a distinguisher, but the main result is that we have a complexity that will be sub-exponential in n over log n. So we see something, the blue problem, it is a very classical problem. There was a lot of incremental improvements. On the other hand, the red problem, it's of algebraic nature, and we see that there can be sudden leaps that could be potentially devastating. So now I give a little more detail. So for us, the GOPA code, we will define it from the dual, the parity check matrix. So we need a sequence of elements in an extension field, F2 to the m, and we need a polynomial of some degree, t, and we construct a Vandermonde matrix. So I call it the private parity matrix, so you can see its form. So it has size t times n over the extension field. And now F2 to the m, we see it as F2 to the m. So this transforms it into a matrix of size mt times n, but over the small field. And then we reduce this matrix. So we see that we have a very, very algebraic structure defined in terms of polynomial, and we try to hide it just with a linear change of variables. So this is very similar to what we have in multivariate cryptography. So in this way, we obtain the public parity matrix, and we have two problems. Either we can try to, so the recovery problem is to find some x and j that produce this public matrix, or an easier problem is only to decide if this matrix or another matrix comes from such a structure. So it's not obvious that it is easier, but I can solve the second problem, but for the moment I cannot solve the first one. So the main ingredient will be the use of quadratic relations in the code. So what is a quadratic relation? Is that a linear combination of products of code words that evaluates to 0. So you can evaluate polynomials at the basis element of the code. And formally, if you consider quadratic forms you evaluate at this basis, then the kernel of this evaluation map is the set of the space, actually, of quadratic relations. So because the kernel of the map is related to the rank of the map, you have this formula that relates the dimension of the space of the quadratic relations with the rank of the evaluation map. And just to give an example, you remember the private matrix that was a Vandermonde matrix. So it generates what we call a Ritz-Solomon code. It has a basis that is in geometric progression. And if you have a basis in geometric progression, then you have relations of this form. CA, CB is equal to CC, CD, when A plus B is equal to C plus D. So formally, this means that the polynomial XA, XB minus XC, XD is in the space of quadratic relations. So if you look at this polynomial, it looks like a 2x2 determinant of a matrix XA, XA, XC, XD, XB. So try to remember this form of quadratic forms. So there was a first distinguisher, so 15 years ago. So it says that if you have such a dual Gopa code, that is a code spanned by the public parity matrix, then we have a lower bound on the number of quadratic relations. But on the other hand, for a random code, we have an estimate on the expected number of quadratic relations. And if we have more structural relations than relations that come just from the dimensions, then we can distinguish in this case. And if you put everything together, you see that this works only when n is larger than kk plus 1 over 2 minus this t. So for this distinguisher to work, we need the length of the code to be quadratic in the dimension. So that's not good. And we would like to have other invariants than the dimension of the space of quadratic relation that could help us to distinguish still. You can observe that if this relation, if this inequality is not satisfied, the algebraic relation of the determinantal form, they are still there, but just they are overwhelmed by other types of relations, but they are still there. And what we want is to find some way to detect them, even if they are only a small part of this space. And the idea, the tool that allows to distinguish, I found it when I was reading a book, so it is at the beginning of the book. And when I saw this theorem, I was enlightened because immediately I saw that it was what we wanted. This theorem is a distinguisher because so it says something about Betti diagrams of points in a projective space, but it says there are two possibilities. When you have two possibilities, you distinguish between two possibilities. And it is about 7 points in P3, so a vector in P3, actually it's given by a vector of length 4. So if you have 7 points in P3, you have a matrix with 4 rows and 7 columns, so it generates a 7-4 code. And it says that in the second case, the code, so the points, they are on a certain curve, and you can, if you know a little bit of algebraic geometry, you know that this curve, it is obtained by evaluating the function 1, x, x2, and x3. So it is exactly saying that these points, they are the columns of a Ritz-Solomon matrix. So now if you look a little more closely at this theorem, there is a 3 in the 1-1 position. So this 3 is exactly the number of quadratic relations. So we are in the case where we cannot distinguish just by the number of quadratic relations, but we can distinguish with another number. Here the 2, or the 0. The 2, actually, it's the number of CZGs between these quadratic relations. So I will give a little bit more. So we will be interested in, or maybe I will swap. So this, so here I explain more generally what was in the previous slide. So these Betti diagrams, so to any code we can associate a set of points in projective space. So the space of quadratic relations, they are just the quadrics that go through these points. On the Betty diagram, what it encodes, you start with some object, you define it by generators and relations, and then these relations, you try to find relations between these relations, and so on. And so this Betty diagram, it encodes, it just a way to write the number of relations of each degree that you have in this recursive way. So what we will be interested, it will only be the first row of this diagram. It is what we call the linear strand of the diagram, and it's something that we can explain in very concrete terms. So I go back to the previous slide. So what is this linear strand? We start with a basis of our space of quadratic relations. So this is a basis, so it means it does not satisfy any linear relation with scalar coefficients. But these are polynomials, so instead of relations with scalar coefficients, we can try to look at relations whose coefficients are polynomials. This is what we call CZGs. And we will, to keep it as simple as possible, so we will only consider relations whose coefficients are polynomials of degree 1. So we consider a basis of these relations, but now we have a basis of relations. This means they do not satisfy any scalar relation, but this L1, L11, L1m, they are polynomials, so we can try to look at relations between these relations that have polynomial coefficients. And, okay, let's keep it simple. We look only at these relations whose coefficients have degree 1, and then we iterate, and this is how we construct recursively this space of what we will call linear CZGs. So, where comes the idea of introducing this object? Well, you remember that for the private matrix, we had quadratic relations that were 2x2 determinants. But now, if we have a more general Gopa code, it contains long Ritz-Solomon codes, so it will contain long geometric progressions. So the space of quadratic relations will contain 2x2 minors of a more long matrix. And so it will contain quadratic forms that have this form, Li, L prime J minus Lj, L prime I. And then it is easy to construct linear CZGs between this quadratic form. Just you take 3 columns of the matrix and you duplicate one of the 2 rows. If you have a 3x3 matrix with 2 identical rows, its determinant is 0. But when you expand the determinant with respect with one of the rows, you obtain these relations, what I call RIGK. And then you can iterate it, because if you take now a 4x4 determinant with two identical rows, it gives a relation between these relations, and you can continue up to F. And what we will see is that this F, it will be very, very close to K. On the other hand, in the random case, we can see that we can give an estimate on the number of CZGs. Somehow, they will stop at some critical exponent that is roughly K times R, or at another, there are 2, so I only have something conjectural about it, but it is really, really well supported by experiments. So now I will conclude. So how do we now distinguish? Well, in the case of a so what the picture represents is the row of the Betty diagram, so the number of non-zero elements in this row. So in the algebraic case, we see that we have non-zero element very, very far away, very close to K. While in the random case, we have some estimate on where this stops. And so if the first F is larger than the second estimate, then we can distinguish by computing the number of CZGs anywhere up to this distance. But unfortunately, if you compute the complexity, it will be exponential in K or in N. But recall that F is very close to K, and actually it's really very, very, very close to K. And what we can do is shorten the code. So what is shortening? You put the code in systematic form, and just you remove the first row and the first column. So it acts in this way on the parameters. It makes N, K, and also F becomes smaller. And now when we perform this shortening operation, we can see that you can do that up to this a certain number of times, but in order to attain this situation where the GOPA case is just slightly more than the random case. And what is nice is that now your new K is much smaller than the previous K. And the complexity now, it is a little bit ugly, but it becomes sub-exponential in n over log n. So with that, what can I do concretely? I am able to distinguish codes with these parameters. So n is 2 to the 10. And so the code, the original code, has parameters 2 to the 10 and 100. I need to shorten it 40 times, and I am able to distinguish it. For classic Michaelis parameters, it's still, so you see that the parameters of the code, they are not that greater than maybe 3 or 5 times greater. So it's still, it looks attainable, but for the moment, the complexity is is quite too large. This comes from the fact that the asymptotic gain, if you look at it, it's log n cube over log n. So it's it turns to 0, but it's ridiculously slow. So to conclude, so I did not break Michaelis. I never pretended that. But I don't know if it will be broken soon, but I would not bet in any direction. It's very, the only thing that I can say is that our understanding of its security is not stable. There are a lot of progress from this algebraic approach. So the main two ingredients, so we use a CZG, so it's something very fancy. When you see it, you love it. But you should not underestimate the second ingredient, is that this F is very, very close to K, and so it allows us to shorten a lot. So now there are a lot of things that we could do. In particular, we have this new hammer, the Betty invariant. And when you have a hammer, everything becomes a nail. So maybe you would like to try to use it in other problems. So I will stop there.
Is there any question?
Very nice results. During the real-world cryptography conference, there was a talk in which it was stated that the French government no longer recommends classic Michaelis due to both published and unpublished results. I assume that the published results are yours. What are the unpublished results?
I think this was not. It was over-interpreted. So, as far as I know, there was no official position from the first government or from ANSI. The talk was an internal view of the cryptography lab. So it's not an official position. As far as I know, so I don't have, I don't have a secret result hidden in my sleeve. As far as I know, there is nothing that breaks Michaelis now. I'm still examining the two ideas that are here, and I think there are more things that can be done, but for the moment, I certainly have nothing concerning that breaks Michaelis.
Thanks.
Yeah.
Thank you. If there is no question, let's thank Hugues again.
Okay, then we move on to the second talk of this session. This talk is on exciting results that bridge between block cipher cryptanalysis and security concerns in deep neural networks. This is a joint work by several people, and we're happy with Adi Shamir giving the presentation.
First of all, I would like to thank the program committee for selecting the paper and showing that there is no age discrimination for old folks like me. So the problem that I'm going to discuss is something which is very natural. Deep neural networks are everywhere. They are highly valuable assets. It can cost sometimes hundreds of millions of dollars to train. And developers often provide these networks not in open source form, but as a closed source form, but with an API. So people can provide queries and obtain the answers to those queries. And the question is, can you recover a deep neural network from its answers to chosen inputs? So this belongs to a very long list of inversion problems where networks are defined by weights. So given weights, it's very easy to determine behavior, but given behavior, can you recover the weights? So this question can be divided into how many queries are needed and how much time is needed in order to fully recover all the weights of the network. Now, the similarity between deep neural networks and block ciphers was first pointed out by Carlini et al. In a very nice paper from Crypto 2020. If you look at it, then in block ciphers, for example, you have a vector of input bits, and then you alternately apply a linear mixing and then a non-linear operation, S-boxes. Linear mixing, S-boxes. This is a classical structure, for example, of AES. If you look at how deep neural networks operate, they look superficially very simple, except that the inputs are numbers, real numbers, rather than bits. You have linear mapping over real numbers, and then the non-linear part is not an S-box, but something very simple. It's a ReLU function, which is obtaining real valued input. If the input was negative, the output is 0. And if the input is positive, the output is the same as the input. So if you think about it as a graph, it's a straight line and then bends upwards. And you repeat it a certain number k of times, and then you are getting an output either of bits or of numbers. So not surprisingly, Carlini et al. Started looking at methods of using differential cryptanalysis and other techniques in order to try to recover the weights the same way as we try to recover the keys from the structure of block ciphers. Okay, now the paper I'm presenting today is the culmination of more than 30 years of effort. The whole area started when in 1993, Ron Rivest and Avrim Blam had posed the question and showed some initial complexity theoretic results about it. And then a very famous Fields medalist, Charlie Fefferman, had shown that given the full transformation from inputs to output, you can uniquely recover all the weights up to a certain unavoidable symmetries. But he didn't give any complexity theoretic result. So in Eurocrypt 2024, last year, I presented another result, and in a moment I'll show you the difference between our Eurocrypt 2024 and the Eurocrypt 2025 results. And this time we are finally solving the problem in its hardest possible scenario. So what is the difference? If you look at what was given to the opponent, to the attacker in last year's paper, given an image, it was processed by the deep neural network, and then you were given a vector of numbers. And if you know the numbers, then you could manipulate those numbers and recover the weights. However, in Eurocrypt 2025 paper, the one I'm presenting now, you are no longer given the logits, the numeric value of the output. You are only given the final decision of the classifier, for example, that for this particular image, the most likely class is dog. So you are only given words. How can you take a bunch of words and translate them into very, very precise numeric values for the weights? So I was very skeptical when we first started thinking about the problem that you can do anything in this model, which is considered the hardest model and the most realistic one, because in most cases, if you are given API access to a deep neural network, you are only given the final decision, not the exact vector of probabilities for the various classes. Okay, so the problem was studied by Chen et al. In Asiacrypt 24, And he showed that it can be solved with polynomially many queries, but his algorithm ran in exponential time. And here we finally solved this long-standing open problem by showing that you need only polynomial time and polynomial query complexity. And our techniques basically demonstrate that even when the only thing you can analyze is the geometric shape of the decision boundary between the class of, say, dogs and the class of cats, that's the only thing you can explore, that's enough in order to determine all the weights of a deep neural network. Quite surprising. Okay, what was the basic tool that we used in our Eurocrypt 24 attack? Critical points in the input space. A critical point is defined as any point in the n-dimensional input space so that the input to one of the ReLUs somewhere in the network is exactly 0. So if I'm going through a critical point, one ReLU somewhere is changing from one behavior to another behavior, like being all 0, and then suddenly it starts growing. So in the vicinity of any non-critical point, all the ReLUs are strictly on the negative side or strictly on the positive side. So you can replace them either by 0 or by the identity function. So the whole behavior is just a composition of linear mappings, which is a linear mapping, or an affine mapping, to be precise. So in the vicinity of non-critical points, you have affine behavior. But as you cross some critical point, you get another affine behavior, but a different one. So you can think about the whole input space as being divided into cells, convex cells, and inside each cell, you have the fixed affine behavior, and the n-1 dimensional hyperplanes, which are cutting across, dividing between cells, are exactly those places at which some ReLU was exactly 0. So if I go from one cell to a neighboring cell, I switch to a different affine behavior. So our basic tool was to start from one image, x1, for example, of a dog, and then go towards x2, which is an image of a car, and I go in a straight line in the input space. And when I go in a straight line in the input space, the function now becomes much easier. Instead of being a function over a huge number of parameters, it's a function of one parameter, which is where you are along this straight line. You have some time parameter going from 0 to 1. So if I look at how the logits, the numeric value of the logits coming out, behaves, you have linear behavior while you are traversing the first cell. And then you suddenly change direction because it's a different affine mapping, and while traversing the next cell, you have a new direction, etc. So you have piecewise linear line, and you can, if you watch it, you can easily identify the critical points, which are the points at which behavior suddenly changes. And this is wonderful, because this is a side channel information. You know, in side channel, you are given information about the middle of the computation, not about ciphertexts. Trying to break crypto systems given only plain text ciphertext pairs is difficult. But trying to break it when you have access to all kinds of intermediate values makes life much, much easier. So here I'm getting a leakage that some value in the middle of the encryption or the evaluation of the deep neural network was exactly 0. Now there are still many questions how you can utilize it, because you don't know which neuron flipped. You need techniques how to identify if this neuron was in the first layer. If you identify all the neurons in the first layer, you can now throw out this first layer and continue attacking the second layer, etc. So there are many, many details which I'm ignoring now. And this kind of side information gives us one affine equation. Whenever I'm crossing a critical point, and critical point belongs to neuron number I get an affine equation that the output of the affine expression was exactly 0. If I could compute n such affine equations for the same neuron, I'll be able to solve it and then recover all the weights. Okay. Unfortunately, all these beautiful tools are no longer available in the hard label case because I'm only told this is a dog and this is a cat and this is a car. Let's look. I cannot compute numeric derivatives and find where the direction of this line switched. Consequently, we no longer get the side information about critical points, totally unavailable to us. And the only thing I can still have are decision points. Decision points are the points at which on my traversal from a picture of a dog to a picture of a car, the decision I get from the output switched from being a dog to being a car. So let's try to analyze what is available and what is not available to me. So decision points and critical points are totally different. Decision point is x2. I hope you can see it. I'll point it out. So the critical points are the black lines. Okay, they divide the input space into cells. The decision boundary is the dotted lines, and it's an n-1 dimensional manifold, piecewise linear, and it divides the whole input space into a region where the answer given to you is a dog, and another region where the answer given to you is a car. So on my traversal, from a picture of a dog to a picture of a car, I encountered x2, sorry, but x2 is not a critical point, and therefore it will not leak to me the information about an internal ReLU. At most, it will tell me that the last logit for a car had now increased above the logit for a dog, but it will at most tell me information about the last layer of the network. So this is not enough. On the other hand, on my way, I crossed many critical points like x3 and x4, but I'm not even aware of them, of their existence, because on my way, even though I started from a dog, I get dog, 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 suddenly I start getting car, car, car. I don't notice that I've passed through the critical line. So what do? We have a new notion which we call dual points. Dual points are simply decision points which are simultaneously also critical points. So if I go back to the picture, which points are going to be dual points? This is a dual point because it is both on the dotted decision boundary and on the critical line. So if I'll find those dual points, they will also serve as being critical points and will enable me to use some of the techniques we developed last year. But during my traversal, I don't go through any dual point. Okay, so dual points is the intersection of an n-1 dimensional manifold, piecewise linear manifold, representing the critical points, and the n-1 dimensional manifold representing decision boundary. By the way, I didn't mention it, but within each cell, a decision boundary is straight. It cannot bend in the middle because it is only, the total behavior is a linear mapping, and therefore you are just looking for when is one logit bigger than another, everything is linear. Yes. Okay, so what do we do? Here is something that will explain the first basic idea. I'm going to start from x0, which is a dog, and go towards x1, which is a car, in a straight line. The decision boundary is the dotted line. I discover the point x2, which is not a dual point. It is decision point, but not a critical point. But what will I do? I'll move in a random direction, a small distance, into x3, and then I'll ask about x3. x3 happens to be in the region which is dog. So now I'll reconnect x3, which is a dog, with x1, which is a car. And again, I'll find a point at which it will intersect the decision boundary. And this is going to be x4. So now I've discovered 2 points, x2 and x4, which are on the same small patch of criticality. And given 2 points, I can extend a straight line and go in the direction until suddenly I leave the decision boundary. And that's the point at which I'm also critical, because only criticality can change direction. So this was one of the major ideas. Second part of our attack, once I have dual points, I have also, in particular, critical points, and I'll apply the old techniques. But we also have to find, once I find the direction of any one of the neurons, I have to decide which side was the positive and which side was the negative. Without it, I'll not be able to calculate what is the total effect of the first few layers and discard them. So what do we do there? We have a new idea. I need a proxy for a neuron being on the negative side and a neuron being on the positive side. So I'm doing something which is to try to agitate the input, move it in a certain direction, which is going to maximally agitate the output of the linear mapping of the current neuron. I already know the direction, but I don't know which side is positive and which side was the negative. So it turns out that if you agitate it strongly and it was on the negative side, this agitation is going to be blocked. It will not be passed. It will remain 0 all the time. While if it was on the positive side, the agitation will continue and create big agitation later on. This will create now a situation in which the size of the linear patch of the decision boundary on the positive side is going to be narrower than on the negative side. Why? Because things are moving in all directions. Some neurons were already on the positive side and they increase, so being faster or slower doesn't matter. They will continue to increase. But if they were positive and now they are decreasing, then if the change is rapid, you will reach the 0 value more quickly. Think a little bit about it, but this serves as a very good proxy for whether you are on the positive or negative side, measuring the width of those patches. It turns out that on the positive side, you are about 20%. It's a constant. 20% narrower than on the negative side, and this is enough in order to do a statistical analysis and find out on which side you are. So this is experimental verification of our new attack. We actually ran it on a 4-layer network with about 1 million parameters, and we managed to extract all of them correctly. And it's the only paper which talks about a realistic number of weights in a multi-layer network and doing it in polynomial time. Concluding remarks, in this talk we developed the first polynomial time extraction attack on deep neural networks, which is when it is in the hardest possible case, you are only given the realistically available label of the classifier. And we demonstrated the correctness by working on a CIFAR10 DNN and extracting all its weights. So it works in practice, not only in theory. And one question I'm always asked is, OK, can you extract all the weights of ChatGPT 4.5? I cannot do it, extract the trillion parameters, because at one point our algorithm requires quadratic time algorithm, and quadratic in trillion is quite a big number. Thank you very much.
We can take a couple of questions.
Hello, thank you very much for the talk. I'm just interested, do you require to know the structure of the network for the algorithm to function, or?
Okay. If you want to make the description of our attack simple, you assume that the structure is known, but we have all kinds of extensions where we find the neurons one by one, and if for a while we went through the input space in different directions between pairs of cats and cars and never discover a new direction of any neuron, then we can stop searching for it. So it's a coupon collector problem, and if you work sufficiently long and don't discover anything new, you can stop, and therefore we can work on arbitrarily large and unknown width. Concerning the depth, again, I don't have to know it in advance, because at every point I see whether I'm recovering the network layer by layer, and at any point I'm just asking, is the current known part of the network enough in order to explain, to provide the given outputs? When the outputs are correctly given, I stop searching.
Thank you.
Is there a question down there?
Yes.
Please go ahead.
Hello, thank you very much for your talk. I was wondering, I guess you've heard that there have been some attacks on, for example, ChatGPT like AI that consisted in asking the LLM to give private information that were used to train the AI, and it's worked successfully. I was wondering if this kind of attacks could be improved with the kind of information that you are able to retrieve from your DNN models.
Okay, so I want to clarify, our attack was on plain vanilla deep neural networks and not on LLMs. The reason is that LLMs have discrete inputs. The inputs are sequences of tokens or words. This is the prompt, and the output is the next word. So I have no way to calculate exactly the transition point. I was assuming that I have a continuity of values in the input space, so I can find exactly where I went from class 1 to class 2. LLMs have different structure, and this is an open problem, and you're all invited to start thinking about how to extract the weights of an LLM. Probably much harder. Thank you.
Thank you very much.
So we can take one more question down there, please.
Yes.
Hi, yeah, if I'm not wrong, in the adversarial machine learning literature, there are these techniques for trying to clone a target model where you just train a model on the inputs and outputs of a target one. How does your attack compare to those in terms of efficiency?
So several answers. First of all, forget about the given attack or cloning something. Just, if you have a large number of pictures of cats and cars, you can create your own network. Here, all these cloning attacks are, first of all, not going to be precise. They are going to have some error in them, while our attack is precise. It will give you exactly the same behavior for all possible examples, those which are in the training set and those which are not in the training set, because they find the directions of all the neurons. And so I cannot compare a situation in which you have an approximate algorithm and one which does not seem to be any faster than training on your own, because basically you're only getting from the training network the labels. And if you already have a database of labeled pictures of dogs and cars, you don't need the training one. And finally, there is no guarantee on its success. Do you need polynomial? Do you need exponential number of training examples? There is no analysis I'm aware of that will give you such bounds. Our case, it is probably a polynomial time attack.
Right, thanks.
Okay, if there are further questions, I'm sure you can catch Adi in the coffee break. So let's give another round of applause to Adi.
So the last talk of this session is by Ward Beullens, and so it's an early career award. So the award is given to people from a PhD or master student up to 3 years after his PhD defense. And so Ward defended in 2022, but it submitted in 2024, and so it's elected to this award. So thank you, Ward.
Yeah, thank you. I think everybody can hear me, so let's get started. So I'll start with a one-slide summary of my talk. So I'm going to talk about SNOVA. SNOVA is a multivariate signature scheme. It's in the second round of the NIST competition for additional signatures. It has very good key sizes and signature sizes, but is because they use a new ad hoc design, so it's a very good target for cryptanalysis. Right, so that's what I did in this work. And I found that actually SNOVA uses the same technique as Mayo. Mayo is another multivariate signature scheme in the same competition, although they don't exactly use the same technique. They use some structured version of it, and this extra structure leads to new vulnerabilities. Like in some cases, it reduces the cost of a 4G attack by up to 40 bits of security. Yeah, that's not quite good. But even worse, there are some very severe weak key attacks. So that means when you generate a public key, there's a small chance that this key is actually weaker than other keys. And like in one of the cases for the security level 1 parameters, there's a chance of 1 in 143,000. So that's quite small, but not cryptographically small. And if you have bad luck and you generate one of these weak keys, then you can forge signatures for this public key in a few minutes on a laptop. Okay, so that's the summary. Like I mentioned already, so I found that Snova uses this technique used by Mail. So that means that now you can put the 4 multivariate signature schemes that are still in the competition in a nice diagram like this. So in the upper left corner, you have oil and vinegar. This is the oldest scheme still in the competition. So this one is very nice, but it has the drawback that the public keys are kind of large. And then the other schemes are variants of oil and vinegar, and they use 2 orthogonal techniques to reduce the size of the public key. So one technique is the whipping as used in Mail, and the other technique is by using algebraic structure. So it's on a high level, kind of similar to how you can use ring LWE instead of normal LWE. And then you can see that Snova is actually just a combination of these 2 orthogonal ideas. So that explains why it has such small public keys, because it uses both ideas, but it also means that it has a larger attack surface. Okay, so in the rest of the talk, I will first briefly explain how oil and vinegar works and this Mayo whipping technique. Then I'll tell you that Snova is actually using this whipping technique from Mayo, and then finally I'll talk a little bit about the new attacks. Okay, so what is oil and vinegar? So it's a multivariate signature scheme, and it uses a multivariate trapdoor. So a trapdoor is a multivariate quadratic map. So a multivariate quadratic map is just a sequence of quadratic polynomials in a number of variables. So here on the slide, I have a small example with 2 polynomials in 2 variables. But typically, we use many more equations, like on the order of 50 equations in at least 50 variables or something, depending on the size of the finite field that you're using. So of course, anybody can evaluate these polynomials efficiently, but going the other direction is hard. Like if I give you an evaluation of these polynomials, it's an NP-hard problem to find a solution, and also on average is believed to be hard even for quantum computers. Right? So this is maybe a good problem to base post-quantum cryptography on. And so this gives you a one-way function, but actually you can make it into a trapdoor function by inserting a linear subspace O on which all these polynomials vanish. So it turns out if you know such a subspace, then you can sample pre-images for all the outputs in polynomial time. So it's also believed that you cannot find, at least for some parameters, it's hard to find this subspace if it exists. Like typically it doesn't exist, of course, but if it's deliberately put there, it's hard to find for some parameters. So this gives you a trapdoor function, and then you just turn it into a signature scheme with the usual full domain hash technique. Right, so this gives you a very nice signature scheme. It's called oil and vinegar. It's already quite old. So this is like the basis of all the other schemes that I'm talking about today. I already mentioned this. So the main drawback of oil and vinegar is that the public keys are quite large. And this is because your public key is this system of quadratic equations. And the number of variables has to be at least 2 times the number of equations. This follows from some attacks. So yeah, you have just a bunch of polynomials. The polynomials have a lot of variables, so it just takes a lot of space to represent all these equations in your public key. Right, so people try to come up with better versions of oil and vinegar where you have smaller polynomials. So now I'll explain how Mayo does this. So the idea is quite simple. So instead of just having this big system of polynomials, you start with some smaller system of polynomials, which I call P here. So this P vanishes on some oil space, but it's a smaller oil space. Right? And then instead of using this P directly, you cannot use it directly because it's too small. You're going to just send the small one to the verifier, and the verifier whips it up on his side before he does the verification. So you somehow make a bigger system of polynomials, which I call P star, which has a factor K more variables. And then you do it in such a way that your bigger map still vanishes on a big enough oil space, and then you can use this public map as your public key, basically. Right. So the most naive thing you could try to do is you just define your P star as just K independent copies of P, and you add them all together. So this, of course, increases the number of variables by a factor K, and it still preserves this vanishing on an oil space, right? Because if your small p vanishes on a space O, then your P star vanishes on this larger space O to the K. Right, but it turns out this is too simple. This is not secure. So we have to do something a little bit more complicated. So instead of just adding all the independent copies of P together, you first have to multiply them by some E matrices. I call them emulsifier because they prevent your thing from collapsing. And also you have to add some other some bilinear maps to have all the cross terms between all the variables, but that's not super important. But what is important is that these matrices that you pick, these emulsifier matrices, you have to pick them in such a way that non-trivial linear combination of them, they always have full rank. Because if that's not the case, then there are attacks. And this will be important later. Okay, so that was Mail. And now I turn to SNOVA, or it's also called Supernova by some of the designers. As I mentioned, it has very small public keys, like 1 kilobyte public keys and 250 byte signatures. So that's quite good. SNOVA stands for Simple Non-Commutative U of V with Randomness Alignment. But as you'll see, the simple in the title is only aspirational. So yeah, this is a slide to try to explain how it works. I already tried to make a little bit more sense of it. So the public key is basically just a bunch of bilinear forms. They have some structure, but I'm not going to explain how they work. And then the actual trapdoor function that you built out of this, it has this complicated formula here. I call it P star in analogy with the Mayo thing, and it's just something like this. So it's a sum of some matrices, and each term in your sum is a product of some green matrices. These are generated from a random seed, so they are random matrices with some structure. The black matrix is your public key, and then there's two red matrices, and these are matrices whose entries are variables. So as you can see, the red matrix appears twice in each of these terms, so that means that the entries of this matrix will be quadratic polynomials in these entries, and these are the quadratic polynomials that you use as your multivariate quadratic map. Right, so I wish I could give more intuition why the SNOVA authors did it that way, but yeah, I don't really know myself. It looks kind of ad hoc, but yeah, that's the best I can do, sorry. So then in a paper, I tried to make more sense of this, and it turns out that this has some form. You can write it in some other form that is much more similar to Mayo, like as this form that you see on the slide. So there exists some bilinear map B that is derived from the public key. Yeah, and then given this map B, you can express this P star map like this. So you again have k sets of variables as input, and then you iterate over all the pairs of inputs. You plug these into your bilinear form. You multiply each of these evaluations by some emulsifier matrix, and then you add everything together. So that's the structure of a SNOVA public map. Yeah, so this is kind of similar to how Mayo works, except this map B has some extra structure. It's not at all a random bilinear map that vanishes on an oil space. Now it's something much more complicated, but I'm not going to go into this. And also these ERJ matrices, they also have some structure. In particular, it turns out that they are block diagonal matrices, and all the matrices on the diagonal, they are the same. So this is quite bad, because if you remember, I told you for Mayo, these matrices, they could not have rank deficiencies, right? All the linear combination of them, they should either be 0 or should have full rank. And it turns out that this is not going to be the case here. And the fact that these are like block diagonal with the same matrices on the diagonal really amplifies this problem, right? Because if you have a rank deficiency in this small matrix that applies on the diagonal, then your rank deficiency is amplified by a factor of how many times this matrix appears, right? So this is bad. And yeah, we're going to use this to now give an attack. So the attack is we're going to compute pre-images for this map P star, and this immediately gives you an attack on the signature scheme, because if you can sample pre-images for your trapdoor function, then you can sign whatever message that you want to sign, right? So it gives a forgery attack. Okay, so the strategy is going to be like this. So you pick some random offsets, V1 up to Vk, and then you're going to look for a pre-image that has this form on the slides. So the assignment to each set of variables, xi, is going to be vi plus some scalar alpha times some variables x. Right? So in other words, all the variables, the assignments to variables are the same x multiplied by a different scalar, and then you add some offset to it. Okay, so why do we do this? That's because if we plug in this assignment into your map P star, and you only look at the quadratic terms, then the quadratic terms, they don't depend on this V anymore, so the V disappears. And since B is bilinear, the alphas, they move out. So then, in the end, what you get is some matrix, which is a linear combination of these EIA matrices, times your bilinear map B. And now the idea is we have some control over this matrix, because you can pick the scalars. So in the first step, you're just going to pick these scalars, these alpha values, such that this matrix that stands in front of your B has a low rank. And in practice, you can just exhaustively search through all the scalars and look at which one gives you the lowest rank. And then in the second step, you're going to solve for your pre-image. So you're going to solve for the x that gives you the right evaluation of P star that you want. And now, because we made this matrix of low rank, that means that actually you're no longer solving a bunch of quadratic equations, but because if you have a rank deficiency of let's say D, then D of your quadratic equations, you can do some change of some linear transformation of your polynomials, so that some of these equations become linear. And now you're no longer solving just a bunch of quadratic equations, but there's some linear equations and some quadratic equations, and this makes it much more efficient to solve. Right, so that's the idea. So I'll give a small example. This is for some of the security level 1 parameters. In this case, these E matrices, they have 17 copies of the same 4x4 matrix on the diagonal. So this means that the rank of this matrix will be a multiple of 17, so either 0, 17, 2 times 17, 3 times 17, or 4 times 17. And it turns out that you will always be able to find a linear combination of rank almost 3 times 17. So that's the worst case. Those are the most secure keys. And then in this case, this basically means you have to break this, to find a pre-image, you need to solve a system with 3 times 17 quadratic equations. Right? But if you're lucky, you can find linear combinations with lower rank. So, for example, with probability 1 in 500, a probability key will allow for a linear combination with rank 2 times 17. So now, when you do the forgery, you only have to solve a system with 34 quadratic equations, which is already much more cheap than the previous case. So it can do it in only 2 to the 97 bit complexity. And if you're really lucky, so with probability 1 in like 100,000 roughly, you only have to solve a system with 17 quadratic equations. So this is really efficient. You can do it in a few minutes on a laptop. Okay, so what are some countermeasures that you can take against this attack? So what I propose in the paper is to just embrace the Mayo approach, because you know you're using the Mayo technique like implicitly, so you might as well just do it explicitly. You have this map B that you somehow came up with, so you might as well just define your P star as just like this thing that I showed. So it's already of this form, but rather than just using the EIJ that somehow this weird construction spits out, you can just pick it yourself, and then you pick it properly so that non-trivial linear combinations always have full rank. So that's what I would do. Also has the benefit that it like decouples this whipping technique from the algebraic technique, so it gives you more flexibility for parameter selection. It's also conceptually easier to keep these things separately, I think. But yeah, that's not what the SNOVA authors did. They decided to tweak their central map even more, so now it looks like this complicated formula over there. Fundamentally, it doesn't really change anything. It's still, you can still see it as some structured form of Mayo, but because they make it more complicated, also the EIJ matrices that are implied by this construction are more complicated, and in particular, they're no longer they don't no longer have this block diagonal structure, so that makes the attack much less efficient. Right. But yeah, drawback is that you need to rely on some heuristics on the rank behavior of these E matrices, which are very complicated to estimate the cost of the attack. So that's not really nice. Okay, so that's it. So in conclusion, I think the main conclusion is that SNOVA actually is a structured version of Mayo in combination with some algebraic structure. So it's kind of similar to like a combination of QRUOV and Mayo. But yeah, they kind of get the Mayo whipping wrong, so this leads to some attacks. And most importantly, these weak key attacks, which are quite severe. So yeah, and the attack is mitigated in the second round submission of SNOVA, but not in the best, not the way I would do it. So yeah, that's it. Thank you.
Thank you very much, Ward. Is there any question? No. So, since there is no question, I think we will move to the break now. Thank you very much.